The most efficient sorting method we'll cover is called the merge sort. Now you notice right away that we don't have well-defined rows the way we've had with the previous sorts. The way a merge sort works is it initially breaks the list into individual items. Its goal is to then sort each individual list. But when each individual list only contains one item, it's guaranteed to be sorted. So at the end of the first run, so to speak, we have 10 one-item lists. That first sort will always be breaking the list into individual lists, no matter how many there are. Then, on each step of the merge, it's going to merge two adjacent lists. It does this by going through both lists, one item at a time, and comparing the lowest item in each list. Whichever one is lower between the lowest item in each list is added to the new list. So here, the first thing it's going to do is compare the first item in the list that just contains 3 to the first item in the list that just contains 7. 3 is less than 7, so it's first going to move the 3 down. Now that list is empty, so it's going to move the 7 down. For the second pair, 1 is less than 6, so it first moves the 1 down, and then moves the 6 down. For these tiny lists, this is a trivial and simple problem. It's just putting two numbers in order. It gets more interesting once we have lists that have 2 items in each of them. So now it's going to try to merge 37 with 16. It starts by comparing the first number in each list. It finds that 1 is the smallest one, and so it moves 1 down. And now 1 is no longer in that original list. Now again it compares the smallest number in each list, which is still the number 3 from the list on the left, and the number 6 from the list on the right. 3 is smaller, so it moves 3 down. And now 3 is no longer in that list. Now it'll compare 7 and 6. 6 is smaller, so 6 comes down. And now the only item left is in the list on the left, so it comes down. So the result is that the two lists have been merged into one larger list, but that one larger list is itself sorted as well. The same thing then happens with 8, 9, and 0, 5. Between 8 and 0, 0 comes down first. Between 8 and 5, 5 comes down next. And now because the list on the right is empty, we go ahead and move the entire list on the left to the end, and we end up with 0, 5, 8, 9. Now we're merging pair by pair, so at the end of that, we have a list with 4 items, a list with 4 items, and a list with 2 items. And our next task will be to merge those two lists on the right. Different implementations of merge sort might do this a little bit differently. When merging 0, 5, 8, 9 with 2, 4, our first number is between 0 and 2, so 0 comes down. Then it's between 2 and 5, so 2 comes down. Then it's between 4 and 5, so 4 comes down. And now there are no more items left in our list on the right, so the rest of the list on the left comes down. Then finally, we're ready to do our last merge. We compare 1 to 0, so 0 comes down. We compare 2 to 1, so 1 comes down. 3 to 2, so 2 comes down. 3 to 4, so 3 comes down. 6 to 4, so 4 comes down. 6 to 5, so 5 comes down. 6 to 8, so 6 finally comes down. 7 to 8, so 7 comes down. And now we're out of numbers in our left list, so the rest of our list on the right comes down. And we're left with 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, a sorted list. What makes merge sort interesting and efficient is that it's recursive. It recursively splits up a list until it has lists of only one item, and then it recursively merges two lists together. That merge function operates by taking the smallest number at the front of each list and repeating that until both lists are empty. So when we do a merge sort on this list, we're really calling merge on these two numbers, and these two numbers, and these two numbers, and these two numbers, and these two, and then calling merge again on these two, and these two, and then calling it again on these two, and then calling it again on these two, and so on. So we're recursively applying merge. The result is an efficiency of n log n, which is significantly more efficient than bubble insertion or selection sorts. For a 1,000 item list, the 3 earlier sorts would require up to 1,000,000 operations, while merge sort would only require 3,000, making it 3,000 times more efficient. Where does merge sort get this drastic uptick in efficiency? It comes from merge sort's knowledge that each smaller list will already be sorted when it's time to merge them. So it only ever has to compare the smallest values, the first values, from each list. In our previous sorts, we had to compare each value to every other single value. But here, we're only comparing the first item in each list. That drastically cuts down on the number of comparisons we have to make. And that's why this is so much more efficient. Now there are several other sorting algorithms as well, like the shell sort, the heap sort, and the quick sort. And these are all relatively close to the merge sort in terms of efficiency.